Okay guys, so we're gonna solve a little bit more complicated, just a little bit complicated RL circuit. So we have the battery, here's the battery, and we have, let's do a little bit space between these two lines of the battery, okay? You're gonna see in a few seconds why I do so, okay? And here we're gonna have my first resistor, which gonna notify as R1. Here we're gonna have some junction. Junction, I mean I have two options. The first option, we're talking about LL, so it's gonna be an inductor, right? So this is the inductor. And here, the other option is to current to go to L2, another resistor. And right now they join in this junction and go back to the battery, okay? Terminal. So this is the plus terminal, this is the negative terminal of the battery, perfect. And just for simplicity, I want to add some, you know what, let's do it later, it's not that critical. And the first question I want to ask you is, what are actually the currents in this circle? Okay, so first of all, find the different eyes, currents, right, eyes of the loop, okay? So what I want you to understand is, you can guess what I do usually. I'm guessing what are the currents inside this loop, this configuration, and the equation correct me. They tell me if I did it right, I did it wrong, continue this way, just add a minus here and everything is fine. So it's not that complicated, just need to guess what are the currents. Okay, so first of all, I have something going outside of the battery. So this is gonna be my first guess. This is a current going from here to here, and I need to give it a name. So the name I'm gonna give it is actually I1, okay? Why I1? Because it's going through the resistor 1. So to make it easier for me to calculate what is the voltage, what is that and that, so I'm gonna call it the same name. And then I get to this junction. After a junction, some of the electrons, the positive charges, moving here in this configuration. So some of them go that way, some of them that way. So I don't know which is which, but I can give them a name. So this one is gonna be, as I mentioned before, this is R1, so that's gonna be R2. And this one gonna be IL. Why IL? Because this is the current going through the conductor. And then these two currents meet up again here and join up to this current. How we can call it? Let's call it F because it's a final current, I don't know. And then go back to the battery. And to solve what are the currents, what is the relation between them, we can use a Kirchhoff's law. What is Kirchhoff's law? It's KCL, which states that all the currents that go inside some junction must be equal to the current going outside of the junction. And this is kind of a stupid equation, if you think about it, or not stupid, but really basic, this is the word, because forget about Kirchhoff, okay? Think about it logically, okay? If I have some river with a lot of water, and the river is actually split to two rivers, so the contribution of the water that's going to the two rivers must be equal together to the original one. For example, if I have, I don't know, 100 liters per minute that's going in this direction, and then it's split out to 20 liters per minute, and that size must be 80 liters per minute. That's what left, okay? That's what coming into the junction, and then it's split. So the idea is what's going in must be equal to what's going out. We don't expect something to coming out of nowhere, okay? There's no generation of current and no dissipation of current. It's not happening, okay? So if there's electrons going this direction, they're gonna split in some way, okay? The sum of the after the junction and before the junction must be the same. So let's give the junction's name. I'm gonna call this one B and this one F, okay? But I'm gonna add this is not junction, but I'm gonna give it a name. Let's call it A, B, right? C, D, it's gonna be useful F, not E, because I don't want us to confuse the electric field. So F, and this is the final one, G. Okay? So let's do the Kirchhoff's law, or this logic law around B. So if I look at B, what's going in? Going in is only I1. And this must be equal to the sum I2 and IL. So this must be equal to I2 and IL. So this is junction B, right? What's going in junction F? Okay, so in junction F, what's going in? I2 plus IL. I2 plus IL. And what's going outside? I final. Okay, so what I got here, I can see that IF is actually equal to I1. That's what I got from here. So the thing I want to say here and emphasize is, look, I did a mistake. I said there's an extra current, okay? And what I find out that this extra current is actually extra one. We don't need it, okay? It's actually equal to I1, okay? So the equation, Kirchhoff's law, actually fix the solution, okay? So don't worry if you choose many direction, what's up, it does not matter. The equation gonna fix you, but keep and consist doing what you did, okay? Don't change it immediately, okay? That's gonna be wrong. Okay, perfect. So we know this, we know that I1, we have I2, and we have IL, okay? And what's the problem here? The problem is that I have only one equation, you see it? And how many unknowns do I have? I have three unknowns, and I have three unknowns and one equation. So what I can do, I need to find out more equations. And to solve that, we can use, you know, the people that love Kirchhoff voltage law, which I don't like. I actually prefer Faraday law, okay? More basic, more smart idea, and actually hold when you talked about inductance, okay? Okay, let's write Faraday law. If I want to find the current in the circuits. So we can get rid of that, get rid of that. So remember what's Faraday law states. The new Faraday law that we taught, that I teach you today, is the integral of a closed loop, right, of E must be equal to what? To the changing, to the minus the changing of the current L, right? That's what's gonna happen. Perfect. So here, when I put this one inside a water with the soap, right? I can see bubbles. How many? I can see one bubble here. You see this part, and I can see another bubble here. So actually, I can choose two different closed loop, right? I have two bubbles, and it's right that I can actually look at all of this as a one bubble. I can do, but then I'm gonna have only one equation, and this one equation is actually kind of to sum these two bubbles. That's what's gonna happen. So if I want two equations, I need two different bubbles. So I need two more equations. So I'm gonna take this, and let's see the solution for each one of them. So let's clean this one. I want you just to remember that I1 equal to I2 plus IL, okay? We need two more equations. So if we're looking at A, B, F, G, so A, B, F, G loop, okay? I look at this one and let's see what is the, let's clean this. Let's see what is the electric field. The electric field here is over there. The electric field is over here. It's going with the current. It's going with the current, right? In this direction. So let's do the loop. I love to do the loop in the in the way that the current is going. The first current is going like that. Let's do it like this. Okay? So what this is equal? So first of all, I'm going through the battery. So I have minus epsilon. It's a given. Epsilon is the voltage. Then I have the resistor, which means I have plus IR1. Why plus? Because I'm going in the direction of the electric field inside the resistor. And then I have plus, this is I1, important. and then I have plus I2. I2, again, I'm going in the same direction, and I want you to notice, and this equal to minus I dot, but what is the inductor of this loop? 0. There's no inductance in this loop. It's negligible. There is no configuration of inductor only in A, B, F, G, right? So this one is 0. So I got only this, and I can write it in another form. Epsilon equal I1 plus I2, I2. So this is a second equation. And if I want another equation, okay, I can do the same idea to the other loop. What is the other loop? Is this one. Let's color it in blue, not blue, in green, so you can see it. This is the other loop that I want to do, which is a B, C, B, C, D, F, right? And let's do it in this direction. Okay, that's the direction of the loop that I want to go, the DL. So I start from B to C, nothing happened. From C to D, nothing happened, right? Nothing happened from C to D because the voltage here is 0 of the inductors. I'm going with the current, it's okay. And when I go from D to F, nothing happened. But when I go from F to B, what's happening? Right? I have minus, because I go against the electric field that we state, the electric field of the resistor. We declare that the current is in this direction. Minus I2, R2. And this one equal to what? To the current, minus the current, multiplied by the inductor. And we do have an inductor. And what is the current? Actually, it's the current that's going through the inductor itself. So let's be more specifically and put IL. This is this specific current, not I2. It's IL. Okay? And I can write this in another form, which is I2 R2 equal I dot L, right? And then I have 3 equations. 1, 2, 3. I can take this term and put it instead of this one, right? And I can use this idea, okay? I can take this idea, no, you know what? It's okay. This, and what I get this, I get this closed, and let's clean this one. I get this, if I use these 3 equations, I actually getting this final close equation, IL plus IL 1 over L R1 plus R2 divided by R1 multiplied by R2 equal to 1 over L, epsilon over L, and here is R2 divided by R1 plus R2. Okay? So this is the equation that we are dealing with. Okay? And if I'm going to find IL, I can find the rest of the currents in the this configuration. So how can I solve this differential equation? So first of all, I can actually make it a lot simpler. For example, I can see that all my resistance are actually locked up here, right? So I can call it R total. And then I see that I have here some other term, which is R total divided by L. And we said that we can love to call this one 1 over tau, right? Because they have unit of time. And we know for the previous tutorial what is the meaning of this in the equations. And what is this term? This term is actually similar to R total, right? It's R total actually. It's R total. Sorry, here it's plus, and here's the multiplication. Okay, sorry about that. Correct this mistake. And here is like R total but divided by R1. So if I want to write it simpler, I can just write it as I dot L equal I dot L plus IL 1 over tau equal to epsilon, again I have this tau, R1, right? That's what I have here. You see that I have this L here, and here I have some correction to R total, so I can get rid of them and put tau. Okay, so this is actually my equation, which is similar to the previous one that we solved in the previous section, so you can solve it the same way that we did. Okay, we said that the solution is homogeneous and a private one. We declared that the private one is a constant, which was really easy to find that constant. Just to put here a constant, it's die out, one unknown, and you find it. And the second more complicated one is to solve it for homogeneous. And we said that this is an exponent. The solution must be exponent because I see derivative plus not derivative equal to 0. Homogeneous, it means 0. So we can see that we can find what is the coefficient of the exponent, what is the power of the exponent, right? And we found it. Another method which we're going to use is is to find something to multiply this equation. Guys, it's only a trick if you want to solve it. I can say that if I'm going to multiply this equation by exponent integral of, if you have this kind of configuration, first order, see, one derivative first order, and not a constant variable, right? A constant coefficient, right? This constant one, this one is a constant, this one is a constant, and it's not homogeneous. You can multiply all this equation by some constant, and it's going to solve it for you the problem. What is the constant? The constant is exponent in the and the power is integral of the coefficient of the one you want to find. I want to find this term, so the coefficient of what I want to find, dt, right? So if we're going to multiply by this equation, the solution would be obvious. I want to see it to believe me, so this actually equal to t over tau, right? So if I'm going to multiply by this, I'm going to see the solution immediately. So if I do it I dot L, let's do it in another color. Exponent t over tau, and here I have IL 1 over tau E t over tau, so in red. And in the end I have what? The same thing, epsilon tau R1 and E t tau. And it's always the same. Always the same when you do this. What you notice that's up here, I can see something derivative multiplied by something not derivative, right? And something not derivative multiplied by something that is derivative. So I can actually write this complex as this configuration. It's actually t tau IL, and this is like the derivative of it, give you this solution, and this is equal to what we have on this side, epsilon tau R1 exponent t tau. So I can do integral of both sides of the equation, and what I'm left with is the derivative cancelled out, IL, and if I do here integral, I'm getting t over tau epsilon R1 plus c, some constant. I can divide by this term and get the final solution, which is let's cancel this one. Right. So let's cancel this one. We get the final solution, which is IL is equal to epsilon R1 plus some constant, which we don't know it yet, epsilon t over tau. Okay, perfect. So how we can find this constant? What we know happen for inductors, we talked about previous question. Inductors are the laziest as fuck. Okay, they're super lazy. Okay, they don't want to have any change in their life. Okay, when the change is coming, they said, okay, there's no other choice. I must do this change, but I'm gonna do it in my own pace. Okay, I'm gonna take it slowly. I'm gonna do it step by step. Don't harsh on me. Okay, be easy with me. So that's the idea. So if I close this circuit, okay, circuit was open at the beginning. What was the current inside the inductor? Was 0. There was no reason for current to go through the conductor, right? But then when I close the circuit, this IL come to alive, right? And appear, but at the beginning it was 0. So at time, I can be confident and say that in time t equals 0, the current must be 0. And that gives me epsilon R1 plus C multiplied by 1. Because if I put t equal to 1, this is 1, and this is, we said it's 0. And I found that C is actually minus epsilon over R1. So let's write it here. The solid full solution is actually let's do it in blue, is IL equal to epsilon over R1, 1 minus epsilon minus t tau. Okay? So this is solution. So what is the current you saw in the inductor? Let's draw this one up, okay? So the current is actually starting at 0, and in the end, what's it's gonna be like? It's gonna be epsilon divided by R1 in infinity, right? Remember, infinity is kind of saying 5 tau, right? Okay? So what's going on in this circuit, okay? Let's look at it. So when we actually turning on this device, okay, the current is going through R1 and then through R2, right? Through R2. There's no current going through IL, but the inductor getting used to the idea that it's need to have a current inside of it. So the current start to grow. Remember that we have I1 equal to I2 plus IL. Okay, so I2 start to dying out and IL start to reappear until the point that I2 is completely 0. There's no current that go through R2 and all the current go through this one. So how my circuit look like? Okay, so my circuit look like that there's no resistors at all and no conductor at all, only R1. Okay, this is the current that I have. A way to think about it, okay, let's think about that this is a light bulb, okay, this is the resistance of the system, okay, let's say the resistance of the system, and when I turn on the device, boom, I see here a strong light appear to me, okay. This light is actually what voltage this light have. It's a I2, R2, and you have some resistor. Resistivity is actually dissipation of energy, okay. Resistor can be heat device, okay, something that's getting hot, or light, or sound, whatever you want to dissipate the energy of the battery, whatever comfortable to you, whatever you need. So you're gonna see an intense light from this one, but step by step, with time, I'm gonna see that the light get dimmer and dimmer and dimmer and dimmer. Why? Because the current look here and I see, oh, dude, I have some resistance here. Why should I go in this direction? There's a resistance. And you see this path and you say, oh my God, this is the ideal conductor. For me, it's perfect. I can go with no resistivity. Why I should go to other place with resistivity that resist me entering the place? So the current would try to go here. But at the beginning it would not succeed because the conductor would try to fight the change. But in some point, see, some point, it would not feel the conductor also because the conductor gonna get used to the phenomena of current inside of it. So I'm gonna have this current in the end. So that's the idea. You can find each one of them, okay, thanks to this relation. And that was a really good exercise for our L circuits. And right now we can use and get used to solving RL circuit and RC circuit, and you can use both Kirchhoff's law, right? Kirchhoff's law of the currents when you're talking about currents in junctions, if you have the complicated circuit like we have had here, but always use Faraday law, the new one that we taught today. So you can start your homework, and I hope this tutorial was really helpful for you, and see you next week. And we're gonna start one of my favorite subjects, which is weight. See you next week.